Hey guys, welcome to an instructional physics video. I'm Bradford Johnson. Today we'll be talking about capacitors. That's these in circuits. Basically what these are, it's two plates. They're collecting an opposite charge, one positive, one negative, over time in a circuit. Now for capacitors, there's three important times that we need to know about. The first is time is equal to 0. As you can see here, I have written that a capacitor is equal to a wire. What that means is, essentially, there's no resistance here. You can basically ignore it, treat it like a normal wire. That makes it really easy when you're talking about capacitors in a circuit. Alright, now time 2 is it's filling up. I have a lot of question marks here. That's because, well, there's not a lot that we need to know about this time. It's gaining charge. Electrons are starting to fill up on the capacitor. It has some resistance, but it's really hard to know what it is. It's mystery land, per se. It's not really super important. The two important ones are 1 and 3. 3 is when the capacitor is full. That, as you can see here, is a capacitor is equal to a really big resistor, and so the resistance is approximately equal to infinity. And so what that means is essentially it's full now of electrons, and so none are passing through it. So the resistance is essentially infinity for this little section here. Alright, so now I'm going to talk about some of the important equations for capacitors. These are as they appear on the AP Physics equation sheet. Here we have the potential energy is equal to 1/2 the capacitance times the voltage squared. It's important to note that this is the voltage over the circuit that it's on, as a capacitor doesn't have any real consistent resistance. It doesn't really have like a voltage drop over itself, and so that's just important to note. And now these two are related. This is the capacitance of capacitors in parallel is just the sum of the capacitance. What that's basically saying is when you have two capacitors in parallel, like so, it's basically like just one big capacitor. That's a terrible drawing. I hope you get what I mean. It's basically like the capacitors act together in one big capacitor. It's important to note that that's the opposite of the way that resistors work, because resistors in series add, whereas they do what capacitors do in series in parallel. Now what capacitors do in series is 1 over the capacitance in the series is equal to the sum of the reciprocal of the capacitance of all of the ones of the capacitors. And so basically what that means is that capacitors in series are also like one big capacitor, but as opposed to adding more area, it adds a bigger distance between the two of them, decreasing the capacitance, which leads me down to this equation here, which is capacitance is equal to Ke sub 0 A over D. What this means is K is permittivity. Usually we'll have air between capacitors, but sometimes there's an insulating material, and K will be less than 1. But when it's just air, K is just 1 per. That's all you need to know. E is a constant. You can find it on the constant sheet. A refers to the area, so how much can be collected on the capacitor, and then D is the distance between the two capacitors. So like the bigger the distance, less capacitance, greater the area, greater the capacitance. Makes sense? And then finally we have capacitance is equal to charge over voltage. More you'll hear about what the charge is for the capacitance and the voltage, but the main important note here is that any capacitor doesn't have like a set charge that it can have on it. The greater the voltage, the greater the charge on the capacitor. Alright, we're going to move over here now to our problem. So I'm going to be talking about these three light bulbs and these three circuits at time 1 and time 3. It's time equals 0. And when the capacitors are full, in terms of brightness, it's important to note that the voltage drop and the equivalent resistance of these circuits is all the same. So at time equals 0, you can essentially just act like this is a wire. So this is just like it's set up like a normal circuit, light bulb, resistance, and it's got some brightness. Alright, now for this one, it's interesting, since this has no resistance at all, and it's in parallel with this, which does have some resistance, all of the charge will flow through this section, leaving the light bulb completely out. In number 3 here, you can see that the same thing happens, but since this resistance is not the light bulb is getting the same amount of voltage, but there's less equivalent resistance over the circuit, meaning that more charge is flowing through the light bulb, making it light up more. Alright, so now we'll talk about when the capacitors are full. In this one you can see we've got a bad scenario. So the current has completely stopped, there's infinite resistance, light bulb is off, that's no good. And then in 2 we can see here that it basically is the same as the first one was at time equals 0. This is essentially not here anymore because the resistance here is infinity, and so all of the charge will be flowing through this section. And so it's just the same resistance, the same voltage. It'll be as bright as this one was at time equals 0. And then we have 3, which will also be the same thing, as you can see, because this will have infinite resistance, so all of the charge will flow through here, making this light up the same as this at time equals 0. Thanks, and I hope the video was informative.